In September 2008, after decades of anticipation, the world's most advanced high-energy particle collider, the Large Hadron Collider, LHC, became operational. Built by the European Organization for Nuclear Research, its construction was painstaking. Over the years, the LHC has significantly enhanced our universe's understanding. However, a recent development has truly baffled physicists. Upon amplifying the LHC to its maximum beam of energy, CERN scientists detected an unexpected and anomalous result. Since then, the scientific community has been buzzing with theories attempting to explain this anomaly. What happened that was so catastrophic? And what are its implications for us in the present and the future of the scientific enterprise? Stay tuned as we discover all this and more secrets. The mind-boggling machine deep underground. Ever imagine a massive machine, so vast it spans across 2 countries and dives deep beneath the Earth? Welcome to the world of the Large Hadron Collider, LHC, a masterpiece of human achievement built by CERN. This isn't just any machine, it's the world's largest and most powerful particle collider, and its story is as compelling as its purpose. CERN, the European Organization for Nuclear Research, is a beacon of international collaboration and scientific curiosity. Its origins trace back to the post-World War II era. As Europe was recovering from the devastating conflict, there was a growing consensus among scientists and policymakers that collaboration was the key to rebuilding the continent's scientific prowess. In 1950, the renowned physicist Louis de Broglie proposed the creation of a shared European laboratory to rekindle scientific innovation and strengthen peaceful cooperation. Soon after, in 1952, 11 countries came together to sign the CERN Convention, establishing the organization. By 1957, CERN was officially up and running on the border between Switzerland and France. The primary objective of CERN was to research atomic nuclei and their constituents. To achieve this, particle accelerators were required. These immense machines propel particles to near light speed, smashing them together to reveal insights into the universe's basic building blocks. Fast forward to the 1980s, and the idea of the Large Hadron Collider, LHC, began taking shape. As the ambition of scientists grew, so did the need for a more powerful machine to probe deeper into matter's mysteries. The LHC was conceived as the world's largest and most powerful particle accelerator, boasting a 27-kilometer ring of superconducting magnets and detectors. Construction of the LHC began in 1998 and was an engineering marvel in its own right. Situated 100 meters underground, this giant loop required collaboration from thousands of scientists and engineers from all over the world. It took a decade to complete, and in 2008, the LHC was ready to start its particle-smashing journey. But why so deep? Well, apart from shielding the collider from the world above, the depth cleverly avoids the challenging terrain of the Jura Mountains. By doing this, there was no need to dig a massive vertical access, saving a significant chunk of change. After all, who'd want to buy expensive land on the surface when there's ample space below? The use of LHC. But what exactly does this massive underground ring do? In 2010, it achieved its first-ever particle collision at a mind-blowing energy level of 3.5 tera-electron volts per beam. To put that in perspective, it was almost 4 times the previous world record. And that was just the beginning. After some upgrades, it now boasts an even more impressive 6.5 tera-electron volts. Imagine 2 beams of particles racing at near light speed and then colliding. That's the LHC for you. It has 4 specific points where these high-speed particles meet and collide. Around these points, 7 detectors eagerly wait. Each is designed to observe and unravel various phenomena resulting from these collisions. Most of the time, the LHC smashes together proton beams. But, once a year, for an entire month, it turns its focus to heavy ions, like lead. It's like the machine's special annual event. Now, you might be thinking, why go through all this trouble? The answer lies in our curiosity about the universe. Physicists are using the LHC to test some of the most mind-bending theories of particle physics. They're especially keen on studying the elusive Higgs boson and probing the existence of a vast family of particles from supersymmetric theories. Ever heard of hadrons? They're teeny subatomic particles made up of even tinier things, called quarks. Picture them as the building blocks of protons and neutrons. The LHC is named after these because it collides them to produce byproducts. Many of these byproducts exist only for a fleeting moment and can't be studied any other way. So, every time there's a collision in this massive underground ring, it's like a mini Big Bang. Scientists then get a glimpse into the very essence of our universe, its building blocks, and the forces that stitch it all together. The mysterious world of the Large Hadron Collider. Constructed between 1983 and 1988, this underground tunnel is a massive 3.8 meters wide, safeguarded by concrete. Above the ground, there's a building filled with essential equipment. Imagine a room packed with complex control electronics, compressors, ventilation gear, and cooling systems. Now, here's where it gets mind-blowing. The LHC produces around 15 petabytes of data every year. That's a massive amount of information. To handle it, an international collaboration gave birth to a computing grid, built especially for the LHC. This network is a tech marvel in itself. The LHC's main mission is to uncover the secrets of a mysterious particle called the Higgs boson. This particle was like a ghost. It was predicted by scientists, but had never been seen. It was so elusive because of its high mass. The LHC, with its powerful capabilities, aimed to produce several of these Higgs bosons every minute. It's like setting a trap for a rare creature that many believed existed but had never been captured. And the LHC didn't stop at that. Besides hunting for the Higgs boson, it explored other uncharted territories of physics. It searched for supersymmetric particles and other unseen wonders of the universe. However, it wasn't all smooth sailing. Just after it started in 2008, the LHC faced a significant setback. A magnet malfunction damaged many parts of the collider, delaying its tests for over a year. But, once it started its operations between 2009 and 2013, the LHC made some groundbreaking discoveries, including finally spotting the elusive Higgs boson. After its first successful run, the LHC went into hibernation for upgrades, reawakening in 2015, ready for more adventures. Its second run spanned from 2015 to 2018, followed by a pause until it rebooted in April 2022. Now, with a boosted beam energy of 6.8 TeV, this machine's third run is set to captivate us until 2026. The mysterious crack. But something extraordinary happened on July 7 during its third run. Imagine Earth's magnetic field as a protective bubble around our planet. On that day, a mysterious crack appeared in this bubble. This wasn't just a fleeting glitch, either. It stayed open for a whopping 14 hours. Think of a window suddenly left open on a stormy night, letting the chilly winds rush in. This crack allowed a flood of solar winds from the sun, leading to massive geomagnetic storms. The result? Dazzling displays of auroras in the sky. If you're a fan of Stranger Things, you might recall Vecna the monstrous villain. Some fans humorously wondered if Vecna had emerged through this very crack. While that remains a playful theory, the visual treat from the auroras was undeniable. But why did this crack form? The culprit is known as a corotating interaction region, CIR. From the sun, CIRs are vast plasma structures created when different speeds of solar winds interact. Imagine two rivers, one slow and one fast, merging into a tumultuous waterfall. These CIRs, along with other phenomena like coronal mass ejections, are thrown from the sun towards Earth. When they hit, we get a light show, the auroras. In the wee hours of July 7, such a CIR collision led to a lasting geomagnetic storm. The National Oceanic and Atmospheric Administration, NOAA, even noted that this storm was supercharged by a preceding coronal mass ejection. Should we be alarmed by these cracks? Interestingly, experts give a reassuring no. Earth's magnetic field, our protective shield, regularly sees such cracks. These usually close up swiftly. However, recent events show they can linger for hours. Imagine living in a house during a storm with a window that occasionally gets stuck open. Though most of the storm is deflected, some water might ruin the couch. Similarly, while our magnetic shield deflects most space storms, some energy sneaks in. This can sometimes play havoc with our satellites, radios, and power systems. In 2003, Harold Freya likened our magnetic shield to a drafty house. Most storms are kept out, but occasionally, some energy slips through the cracks. Sometimes, just enough to create a spectacle in the sky or to mess with our tech. Thankfully, there were no resulting radio blackouts or power outages. Instead, this cosmic event brought a stunning surprise for the residents of Canada and the U.S. awe-inspiring northern lights. But there's more. Scientists have let us in on a secret: the sun is becoming more lively. In fact, it's showing more activity than they anticipated for this time in its cycle. What does that mean for us? Simple: if you've ever wanted to see an aurora, your chances just got a lot better. Over the next 3 years, expect the skies to dance with colors even more frequently. Workings of the LHC. And speaking of monumental scientific revelations, let's talk about the Large Hadron Collider, LHC. Think of the LHC as a massive microscope, helping scientists observe the tiniest particles in our universe. Back in July 2017, it uncovered several incredible findings, like the properties of the Higgs boson. Fast forward to 2021, and the LHC had identified 59 new hadrons. And in July 2022, a new particle was observed, called the pentaquark, made up of unique combinations of quarks. However, even the best devices, like our beloved LHC, face challenges. Over time, their efficiency in producing groundbreaking results decreases. But scientists have a trick up their sleeves: they upgrade. The LHC is currently undergoing an upgrade, known as the High Luminosity Large Hadron Collider. Initiated in June 2018, this project will supercharge the LHC, making it even better at spotting rare cosmic occurrences. So, what's the LHC's claim to fame? In its first run, it discovered the Higgs boson. The LHC's second run gave even more insight into this particle. Now, with its third run planned to wrap up in 2025, scientists at CERN are hopeful for double the data and, potentially, double the discoveries. The Large Hadron Collider, LHC, at CERN is gearing up for a fascinating journey. Picture this: by 2029, this colossal machine, after much preparation, will be colliding particles at rates 10 times more intense than ever before. The excitement doesn't stop there. This phase, expected to continue until 2042, will collect data sets that are a whopping 10 times larger than what we'll see at the end of its third run. Now, if you're wondering why this is significant, let's delve into the thrilling world of proton collisions. Think of protons as bags of colorful jelly beans. Within these bags, there are smaller particles known as quarks, bound together by even tinier particles called gluons. It's like a dance of nature's tiniest elements. Visualize 2 bags of jelly beans smashing into each other. Most times, the jelly beans, or particles, scatter, reforming into familiar patterns. But every once in a while, something magical happens: 2 quarks or gluons collide head-on. This collision squeezes all their energy into an almost infinitesimal point, then explosively releases it. It's in these rare, high-energy moments that physicists might catch a glimpse of nature's deeper secrets. But here's the challenge: in the LHC, bunches of protons collide an astounding 40 million times per second. To put that in perspective, imagine trying to capture a unique moment from a fireworks show that's exploding non-stop. And each of these collisions results in a photo that's 20 times larger than what you'd snap on your smartphone. Gathering all this data would fill up a database with 1 million gigabytes every single second. That's a lot of data. The reality is, amidst the 40 million events happening every second, most are ordinary. Buried within this data avalanche, there's just one special Higgs boson event. So, how do scientists keep from drowning in data? Enter the trigger, a sophisticated computer system that's like a discerning photographer, selecting only the most intriguing few hundred collisions per second. These are the moments that scientists will later pore over, hoping to unveil the universe's mysteries. The Large Hadron Collider, LHC, is like a colossal microscope, zooming into the very building blocks of our universe. Imagine a massive machine trying to unlock the secrets of how everything is made. Its main goal now? To find never-before-seen tiny particles that could unveil new cosmic secrets. Dark matter and another LHC? Now, some of these mysterious particles could be super heavy. Think of them like heavyweight champions of the universe, decaying into groups of smaller particles, showing off with immense energy. Yet, most scientists believe that during the LHC's third run, or Run 3, we might not find these big guys. Instead, we might catch glimpses or clues, sort of like a treasure hunt where you find a map instead of the actual treasure. These hints might just be the teasers for bigger reveals in future runs. Here's a twist: dark matter. You've probably heard about it, that enigmatic substance in our universe that's invisible but makes up a chunk of it. Some new particles might be related to this dark matter. But they are so sneaky that they hardly ever show themselves directly. It's like trying to see the wind: you can't see it, but you can see its effects, like leaves rustling. In the LHC, we look for other particles moving oddly, hinting at the presence of these invisible ones. However, there's a challenge. Many times, these signs are so weak that our detectors miss them. It's like trying to hear a whisper in a rock concert. But with some upgrades in Run 3, we're tuning our ears, or rather, our detectors, to pick up these faint hints better. But wait, there's more. Plans are underway for an even bigger, bolder machine, the Future Circular Collider. Picture it as the LHC's bigger sibling. This massive particle smasher could cost between 9 and 21 billion euros. However, not everyone's on board with this idea. Some believe that with such a hefty price tag, we should be looking at other big science ideas. For instance, how about a giant radio telescope on the moon's hidden side? Or a device in space to detect cosmic ripples, called gravitational waves? Sabine Hossenfelder, a renowned physicist, argues that this new colossal machine might not even uncover the secrets we're hoping for. It's a bit like investing in a super telescope that might not show us any new stars. Still, with the LHC set for Run 3 and even a Run 4, there's a lot on the horizon. It's like we're in the middle of a cosmic detective story, uncovering clues one by one. And every stage promises more revelations. Think of them like episodes of a thrilling series, and we're about to binge-watch. One such surprise was a recent anomaly in Earth's magnetic field, which stayed open longer than expected. It's like discovering a hidden door in your home you never knew existed. What more will we find next? Max Laughlin's shocking theory. According to geniuses like Max Laughlin, however, we may be in trouble. Max Laughlin's theory suggests that experiments at the European Organization for Nuclear Research, CERN, have caused humanity to shift into an alternate universe, leading to the phenomenon known as the Mandela effect. According to Laughlin, the high-energy particle collisions performed at CERN may have inadvertently caused a ripple in the fabric of space-time, which in turn propelled us into a slightly different version of our universe. The Mandela effect, named after the mistaken belief that Nelson Mandela died in prison during the 1980s rather than in 2013, is a phenomenon where a large number of people remember events or details differently from how they actually occurred. Proponents of the theory believe that such collective misremembering are not mere memory errors, but evidence of our transition to an alternate reality. While Laughlin's theory is intriguing, it remains speculative and has faced skepticism from many in the scientific community. The experiments at CERN are indeed cutting-edge and explore the boundaries of our understanding of the universe, but there's no concrete evidence to suggest they have the power to send us into a parallel reality. Safety protocols at CERN. Yet, with such theories cropping up, the masses start worrying about their safety. At CERN, safety is embedded in every aspect of its operations. First and foremost, stringent protocols are in place to minimize radiation exposure. Personnel working with particle accelerators and detectors are equipped with dosimeters, and areas with radiation hazards are strictly controlled. Robust engineering designs and shielding materials are used to contain radiation. Chemical safety is another vital concern, with meticulous handling and disposal procedures for hazardous substances. The facility also prioritizes electrical safety and fire prevention, conducting regular inspections and ensuring that all electrical systems comply with international standards. Moreover, CERN emphasizes the safety of its workforce. Comprehensive training programs and safety drills prepare personnel for emergencies, including fire, chemical spills, or radiation leaks. Additionally, a comprehensive medical service is available on-site to handle any health-related issues promptly. Environmental precautions are equally crucial. CERN minimizes its environmental footprint, manages waste responsibly, and monitors air and water quality to prevent contamination. CERN's commitment to safety extends to the public, with public access controlled to minimize risks. It maintains open lines of communication with local authorities and engages with the community to address concerns. Thank you for being with us. Make sure to watch the next video on your screen, truly mind-blowing.